In the last video, we took a look at the electric charge, and now we're going to go ahead and take a look at the electrical properties of materials and take a look at polarization. So you can lump, electrically speaking, objects into three categories: conductors, insulators, and semiconductors. Semiconductors, which are the basis of transistors and thus the computers that you're using to watch this very video, in fact, turn out to require an awful lot of modern physics, and so we will defer that to those kind of treatments. But most materials can be lumped into either conductor or insulator. And the main difference is that in a conductor, charges move freely. And our picture of that is if we take a look at, say, some object that's metallically bonded, say copper. Copper's a great example. Let's say you've got some copper. What you have here are some mostly shielded nuclei of copper. And what holds them together, if you remember, is what chemists call a metallic bond. And in a metallic bond, what happens is that all the valence electrons, which I'm just kind of drawing in with this red schmuzzle, are shared in what's called the electron sea. This means, in a certain sense, all the valence electrons in, say, a block of copper, so, what you have in a lot of coins, you can view a coin as almost like a giant molecule, because all the valence electrons are shared in common by all of the nuclei. This allows charge to move very freely and very quickly. And so we talk about charging by conduction. So for instance, if I were to, let's say, have a sphere here, and I were to bring a rod that I had negatively charged so that it touched the sphere, what would happen is that some of the excess electrons on the rod would be transferred to the sphere. And since all of the valence electrons are shared in common, what would happen now is that the electron cloud would actually get slightly bigger than the object. And so you would end up with a net negative charge on the outside. On the other hand, if you were to have a conductor again here, and you were to bring a positively charged rod to it, like so, and you touched it to it, that would actually take some electrons out of the electron sea in order to neutralize the charges sitting on the rod. As a result, the electron cloud that you would have left would actually end up being just a tiny bit smaller than the object, and so you would end up having positive charge left behind from the partially shielded nuclei. So this is charging by conduction. And so what happens is just basically you make the shared electron cloud bigger or smaller. And so the charges get uniformly distributed across the object We say this is charging by conduction. This is different than with an insulator. With an insulator, the charges stay put. So you can put charge on an insulator, but the charges stay put, so they don't move freely. And if they do move from one thing to another, we say that you charge not by conduction, but by transference. So let's say you have a rubber ball here, something like that, and you bring a negatively charged rod to it. What will happen when you touch it is you'll just take a few of the electrons off of the rod and just leave negative charges right where you touched it. And those charges won't move around anywhere else. Okay, so with that as background, let's start to take a look at charge polarization. Oops. So I'm going to draw schematically an object that's called an electroscope. So in an electroscope here, you have a conducting ball that's attached to a conducting rod. And then at the end of the rod are two conducting leaves. Just think thin, lightweight pieces of metal that are, well, first we will have them just hang straight down like that. So everything here is a conductor. Now, what happens is when you bring a charge nearby but not touching. So here we go there. So let's say I bring by a positive charge rod, but we don't let it touch. What will happen is these leaves will now swing apart, even though we didn't transfer any charge on or off of the rod. And if you were to repeat this experiment with a negatively charged rod, exactly the same thing happens. So what I would like you to do at this moment is, again, pause the video here, and I would like you to, by drawing some sketches or something, come up with an explanation for what's happening here. Alrighty. So the deal is, keep in mind that since the entire electroscope is a conductor, the whole electron cloud of the whole thing is free to move. So as a result, you will start to attract some electrons closer to the rod here. But those charges had to come from somewhere, and what happened is the whole electron cloud shifted. So that's leaving these leaves behind, positively charged, and they repel and swing apart. And if you brought a negative rod near but not touching, exactly the same thing will happen, except that you will have repelled the electrons away, leaving behind positive charges here and making these leaves negative. And again, like charges repel. Now, if it happens to be relatively low humidity and you happen to have a rubber comb and some hair available, if you vigorously rub the comb through your hair so that you get like a good crackling sound, what you can do is hold it up next to an empty pop can. You want it lying on its side so that it's free to roll. Hold it next to that empty pop can and just start pulling the comb away slowly from the pop can. When you do this, you should find that you've got yourself a new pet. It's following the comb wherever you want to go. So what's going on there? You could also do the same thing with, say, a small piece of aluminum foil. Again, probably you wouldn't want more than 1/2 centimeter on a side. Probably work better than the pop can, unless if the humidity is higher. So what's going on there? So let's say this is a little piece of aluminum foil right here. And let's just say you bring a positively charged rod over but not touching the aluminum foil. Now again, because the electrons are mobile, the negative charges will end up on the upper surface and will leave behind, because the whole electron cloud shifted up, positive charges underneath. And so the upshot here is that these electrons on the upper surface will feel an attractive force upward, and the positive charge left behind will feel a repulsive force downward. Now notice I didn't draw them the same length. That's because this distance is slightly further away than this distance, so the force here is a little bit weaker than the force here. So if we go ahead and add the two forces together, so here's my force, my upward force and my downward force, they almost but not quite cancel to give you a net upward force. And if you had held a negatively charged object over the aluminum foil instead of a positive, you'd have exactly the same attraction, except that you would have positive charges on the top of the foil and negatives on the bottom, but it would be exactly the same story. You get this attraction. And I should apologize right now, but this isn't even close to scale. These two arrows, I don't know how big this is on your device you're viewing it on, but let's say this was 1 centimeter long. These things here would actually be hundreds and hundreds of kilometers long. The cancellation is almost but not quite complete. And this gives us another clue about the strength of the electric force compared to gravity. Because if you think about it, when you're drinking a beverage, an even weaker version of this effect is happening between your neutral hands and the neutral molecules in your beverage container. And yet, this almost utterly, completely canceled out electric force, leaving just the tiniest little drag behind, is more than enough to defeat the gravity of an entire planet. So the electric force is very, very strong. The reason why we don't see it being a player at large scales is literally because of its strength and the fact that opposite charges attract. If you have too much of, say, positive charge nearby, you'll attract negative charges until basically the region becomes neutral and you made yourself an atom. And it turns out that this effect, although I showed it here with the neutral conductor, this is what was happening with your paper bits in the previous video. So let's say now this is a piece of paper. Although, in the case of the piece of paper, actually let me move that all down here. There we go. Maybe even a little further. Yeah. Okay. So let's say you go ahead and you bring a positively charged rod again over your piece of paper. There is no shared electron cloud in paper. The electrons are confined to stay in their molecules. So what you can look at here is you have, I'm just drawing a bunch of molecules in the paper. That'll do, but it keeps going on. And then what will happen is the electron cloud will shift. So up here, the whole electron cloud of the molecule will shift upward a bit, leaving this end of the molecule here fractionally negatively charged, and this end here fractionally positively charged. Fractional negative, fractional positive, fractional negative, fractional positive. You get the idea. And then what's happening is this very same attraction mechanism is occurring, except it's on an atom by atom basis. On an atom by atom basis, there will be an enormous up force and an almost as big enormous down force, leaving behind a very small net force up. Sorry, those just looked like a mess, didn't they? So again, you'll have this nearly perfect cancellation. In fact, it'll be an even better cancellation than before because the difference in distances is so much less. But even that tiny little bit upward is enough to attract, say, a piece of paper against the force of gravity pulling down on it. So neutral objects can be attracted by anything. All right. So we'll finish out with a couple other quick observations here. One is a property of electric charges called charge quantization. So there's an experiment due to a physicist by the name of Millikan, who was in Ohio in 1909. The name is not spelled the same as the former governor of Michigan, and he is no relation that I'm aware of. The experiment is known as the oil drop experiment. What Millikan was able to do was he was able to put electric charges onto tiny little droplets of oil. He just got the droplets of oil by just putting them through an atomizer is the fancy name, but it's basically just a perfume bottle sprayer. And he had these tiny little oil drops that he was able to electrically charge by having the oil drops pass through a radioactive source. And sometimes the radiation would strike the oil drop and change the either knock some charges on or off, and would put some charge onto the oil drop. Now, the technical details are very annoying, and this is an experiment that tends to make you go a little cross-eyed when you do it. Conceptually, what Millikan was able to do was apply known positive and negative charges here so that he could have a known, so that he could apply an electric force off against our charged oil drop to counter the force of gravity acting on it. Now, ideally, what you would like to be able to do is get these drops to hover. In practice, you can't get them to hover, so what you do is you attract them up, you then discharge these plates here, you let them fall down, and you time how long they go up and down. You have to take air resistance into account. It's a pain. But conceptually, we can just imagine that somehow he got them to hover, which he didn't actually, but conceptually, you can do that. Well, he was able to show, by careful comparison of the electric force off against gravity, that the electric charges had to come in discrete integer multiples of a quantity. This quantity gets, the official name is the quantum of electric charge. Most people call it the charge on the electron, but that isn't quite right, because in physics all constants are positive numbers and the charge on the electron is negative. But we use the symbol E. And in modern units, the charge on the electron is 1.602176634 times 10 to the negative 19 coulombs, and this is an exact number. More on that in a second. And he was able to show that whatever charge you had on the oil drop, it was equal to E, 2E, 3E, negative E, negative 2E, negative 3E. 0 is certainly a possibility as well. It'd be neutral and it'd just fall. But it always came in these integer multiples of E. If something comes in integer multiples of something, we say that it is quantized. Man. Much later, we had to kind of walk that statement back a little bit. It turns out that quarks, which are the objects that make up things like protons and neutrons, they turn out to actually have charges of plus or minus 1/3 E or plus or minus 2/3 E. However, they always are bound together in ways that give you integers, so it was understandable. I'm sorry, 10 to the negative 19 coulombs. I missed the C there, my apologies. And the unit coulomb is a C. Why is this an exact number? This is because back in 2019, the definition of how SI units work was revised. And now all the definitions of things like the meter, the kilogram, the second, all of that harken back to making certain physical constants equal to exact numbers. The charge on the electron is one such thing, and so is now defined to be an exact number. Now, I should point out that a coulomb of charge is a lot of charge, and typical charges of things will be in the nanocoulomb range, which, if you think about it, means you're still having something like on the order of 10 to the billion, about 10 billion excess electrons, or a deficit of up to 10 billion electrons or so hanging out there just to even get your nanocoulombs. So that's quite a bit of stuff. Okay. Now, I'll just finish off with one more note, and that is dipoles. I got it. So we've already seen the induced dipole. That's what happened with our molecules of the paper. So if I have some atom, going to have a positively charged nucleus here. If I put some positive external charge out here, what will happen is the whole electron cloud kind of shifts over. And so that will separate out the negative charge a little bit. On average, the negative charge would be located over here and the positive charge there. So you get a little bit of a separation of charge. And you always, whenever you have a dipole, what this means is you have a separation of charge. In this case, the separation isn't going to be very much. Some molecules, however, are what are called permanent dipoles. And the classic example there is water. So if you have, say, 2 hydrogens and an oxygen, curiously, the angle that the hydrogens make with the oxygen is exactly equal to the angle made by Mickey Mouse's ears. So this often gets called the Mickey Mouse model of the dipole. But what winds up happening is the oxygen is a bit of a electron hog. And so although this is technically a covalent bond, the electrons spend the excess electrons spend the vast majority of their time over here, leaving behind the protons that make up the nucleus. So here, if I were to say bring a negatively charged rod over here, what would happen is the whole molecule would rotate around and then again be attracted. With permanent dipoles, the separations are already, a separation charge is a structural thing. And they tend to be attracted more than induced dipoles because you have to bring them close to bring in the separation to then bring in the attraction. Here, the separation is already a thing. Alrighty, so in the next series of videos, we will start to take a look at Coulomb's law and get quantitative with electric forces. Catch you on the flip side.